Process Control Narrative, a tutorial. Overview of narrative philosophy in process control safety. Process control narratives, PCNs, serve as the plain language counterpart to technical flow diagrams such as PFS and PFS. They function as definitive, structured statements of control logic, implementation intent, and operational considerations for process units. PCNs are not mere supplements, but foundational documents that guide automation vendors, operations teams, and integrators through design, implementation, and validation of control systems. Particularly in projects involving complex loops, multi-vendor systems, or interlocking logic, PCNs bridge the interpretive gaps that schematics cannot address. A PCN includes all relevant control and instrumentation details for normal, startup, shutdown, and abnormal conditions. It allows clarity in configuration for distributed control systems, DCS, programmable logic controllers, PLCs, and supervisory systems, enabling deterministic performance across all operational scenarios. Process control documentation strategy and lifecycle integration. PCNs must evolve through all project phases: definition, implementation, commissioning, and operation. Initial drafts focus on functional intent and are issued alongside PFs. Implementation phase updates capture logic, constants, interface specifics, and operational detail aligned with IN tools or equivalent instrument engineering databases. Any divergence from intended functionality is logged in the history section. Vendor package controls are integrated under the relevant unit narrative to ensure unified documentation. Narrative content structuring and scope. Each process unit shall maintain one PCN and one IPF narrative, covering functional objectives, description of all control elements, simple and complex, operational interface, and abnormal behavior, advanced process control APC objectives, e.g., SMOC, ODS-based non-control algorithms, performance indicators, diagnostics, interactions across subsystems or vendor-specific packages. These narratives include operational modes, control schematics, configuration logic, and diagnostic feedback plans. For each complex loop or sequence, the documentation must detail objective, functional description, operational and implementation aspects, history, and timing, supported by diagrams and pseudocode logic. Complex loop narratives and design rationale. Detailed narratives are mandated for complex logic, beyond single cascade or selector logic, sequence-batched processes, inter-unit or multi-vendor subsystem integrations, loops containing calculations or derived logic. For each, the PCN must specify control objective and justification, functional methodology and tag service mapping, operational modes, startup, steady state, abnormal, crippled, interfaces and overrides, full derivation and source for constants, curves, flow sheets, design sheets, timer rationales, and operator accessibility. This rigorous breakdown enables FAT, SAT, and post-commissioning diagnostics. Logic and sequence control narratives, batch, sequence, and logic control schemes require structured documentation. Narrative flow matching, sequence function charts, SFCs, structured English, pseudocode for program logic, steps, actions, and transition conditions, ignored feedback handling, e.g. failed valve confirmation, interlocks, overrides, and restart logic. Timing charts for complex valve motor sequencing. All sequence programs must be operator accessible, allowing holds, restarts, and overrides where necessary. SFCs must map logic across interlinked sequences, abnormal checks, and fallback sequences for fault recovery. Interconnected subsystem documentation. Systems involving governors, compressors, PLCs, or auxiliary vendors must include a functionality overview narrative, describing total application logic and inter-subsystem signal routing, a functionality overview diagram, hardware layout, functional blocks, signal identification with tag, type, and direction. The system integrator is responsible for compiling and maintaining these documents as part of the unit narrative, not the subsystem vendor. Advanced process control and ODS algorithms. For multivariable control applications, APC narratives must capture controlled, manipulated, feed-forward variables, constraint logic, prioritization, benefit analysis, dynamic behavior under disturbances, crippled mode degradation, and fallbacks. For non-control ODS calculations, e.g., equipment health monitoring, PCNs must outline algorithms, sources, and update logic for ongoing diagnostic support. Design integrity and automation. PCNs must be fully automated documents with word-generated table of contents, section numbering, cross-referenced figures, diagrams, and equations, Visio or AutoCAD-based diagrams embedded in the document, integrated history tracking and versioning. Control diagram figures must align with PEF symbology and be grouped at document end, not interspersed within text. Conclusion: control is a deterministic system backbone. The PCN is not merely descriptive, but prescriptive. It formalizes process control strategy, implementation logic, and diagnostic intent in a structured, validated format. When rigorously developed and maintained, the PCN enables deterministic, safe, and auditable process control performance from commissioning through the entire operational lifecycle. General aspects of the process control and IPF narratives. Purpose and scope of narrative documentation. The process control and instrumented protective function, IPF narratives, serve as foundational engineering documents that define the automation and safeguarding philosophy of a process unit. For each unit, a single comprehensive process control narrative and a corresponding IPF narrative are prepared. These documents ensure clarity across multiple disciplines: process engineering, control systems design, implementation, and operations, and are structured for reuse by operators, DCS IPF vendors, and system integrators. They capture the complete functional description of all control loops, sequences, interlocks, advanced control applications, and safeguarding logic. These narratives support consistent understanding and traceability across the project lifecycle and play a critical role in configuration, testing, operation, and maintenance. Development lifecycle and versioning. Narratives are dynamic, developed progressively through the definition and implementation phases of a project. Early drafts focus on control objectives and functional requirements aligned with flow schemes and project specifications. As vendor data, logic diagrams, and field information become available, the narratives are expanded to include all operational details, interface signals, set point rationales, and timer logic. Contractors draft functional sections early in the project, while implementation contractors finalize operational and integration details. All deviations from original design during commissioning or startup must be recorded in the history sections, ensuring continuity and transparency for future changes. Vendor packages, particularly for rotating equipment or third-party systems, are incorporated into the unit's narrative to provide a unified view. Cross-boundary control logic is also documented to describe signal exchange and control integrity across units or systems. Intended usage across stakeholders. Narratives are used by process designers, instrument engineers, contractors, operators, maintenance teams, and automation vendors. They serve as functional specifications for DCS and IPS vendors, enabling configuration, FAT/SAT testing, and integration activities. The final as-built versions form part of the plant's official design dossiers and operating manuals. Sections of the narrative are referenced during HAZOP reviews, IPF classification, and are often foundational to alarm management and override procedures. In many cases, they are used as training materials or fault analysis tools for plant operators. Transition to IPF classification tools. In later project stages, IPF and alarm narratives may be superseded by structured IPF requirement sheets or safety instrumented function software. However, narratives remain essential for describing complex logic, sequences, or trip rationales that cannot be fully captured by tabulated documentation. In facilities not pursuing formal IPF classification, these narratives remain the primary documentation for all safeguarding logic. Document accessibility and digital structure. Given their iterative nature, narratives are maintained in electronic formats compatible with project systems. They are configured to support automated updates to section numbers, cross-references, and tables of contents. Standardized formatting ensures consistent navigation and readability across units and vendors. Content is structured to allow selective extraction for integration into operating manuals, FAT procedures, or engineering databases. Automation features are mandatory to avoid manual errors in complex, multi-section documents. Treatment of constants and set points. Narratives must include all calculations and constants used in control logic, including their source references, vendor data, process simulations, datasheets, or flow diagrams. The rationale behind each value must be explained to allow traceability and future revalidation. Actual set points, alarm, trip, timer settings are maintained separately within the instrument database, e.g. ntools, with cross-references from the narrative. Supporting documents like timer lists or DCS parameter lists are generated directly from the database. As-built documentation and maintenance responsibility. Contractors are responsible for updating all narrative documents to as-built status upon project completion. After handover, plant operations must maintain the documents in line with process changes, equipment upgrades, or control logic modifications. As living documents, they serve as the definitive source of truth for the plant's automation and safeguarding philosophy. Process control narrative, content and structure, purpose and role in engineering documentation. The process control narrative, PCN, is the definitive written description of a process unit's automation strategy. It supplements process flow schemes, PFS, and process engineering flow schemes, PEFS, by articulating in clear engineering language the intent and logic of control systems, sequences, and calculations. While diagrams provide structural representations, the PCN explains how controls are supposed to work, why they are implemented, and under what conditions they operate or fail. This narrative is structured to guide system integrators, control vendors, process engineers, and operators through configuration, verification, commissioning, and operational troubleshooting. It includes all required information for implementing distributed control systems, DCS, programmable logic controllers, PLCs, advanced process control, APC, and operational data servers, ODS, across the unit. Document structure and scope. A complete PCN for each unit includes background information about the unit's process objective, configuration, and operating modes, general walkthrough of all control schemes used in the unit, detailed narratives for complex or non-standard control loops, logic, sequence, and batch control schemes, overview and functional diagrams for multivariable and advanced applications, narrative coverage of interlinked vendor subsystems, algorithms used in supervisory or monitoring applications not directly involved in control there. This structure ensures that both simple and complex automation strategies are properly documented and traceable, enabling safe, stable, and efficient operation. Background process information. This section introduces the process unit, its purpose, its location in the overall site flow, its connection to other units, and its main operational modes. It highlights key process equipment, vessels, columns, compressors, heat exchangers, etc., and describes how the unit behaves during startup, shutdown, or transitions. This context is essential for understanding why certain controls exist and how they function within the broader system. Control description. This section presents a high-level overview of the entire control landscape. It describes all control loops, logic systems, and batch operations used in the unit. The narrative explains what each loop does, what variables are being controlled, and how the control contributes to process safety, efficiency, or product quality. This walkthrough helps establish a clear relationship between process dynamics and automation strategy. Detailed narratives for complex control loops. For complex loops, defined as anything beyond a basic cascade or override, the PCN must contain a detailed breakdown of the control objective, implementation method, and operational behavior. These narratives include clear statement of the control objective and process rationale, functional description of the loop with tag numbers and service details, operational modes including startup, steady state, shutdown, and failure scenarios, interfaces with other systems, e.g. inter-unit loops or multi-vendor equipment, calculation details including constants, derivations, and supporting documentation, specific operator interface and implementation considerations, historical changes and reasons for adjustments to design. Detailed loop diagrams must accompany these narratives and are included as grouped figures at the end of the document for clarity and traceability. Logic, sequence, and batch narratives. All non-continuous operations, such as valve sequencing, batch filling, or safety interlocks, are documented in this section. Each sequence is broken down into logical steps and documented using step-by-step structured logic in pseudocode or structured English, operator actions and required confirmations, conditions for progression, failure, or holding, interlocks, and overrides, valve timing charts for complex sequences, sequence function charts, SFCs, to visualize logic paths. This section ensures that the sequence behavior is fully transparent to vendors, operators, and control engineers. Advanced process control applications, where APC schemes, e.g. multivariable, model predictive controllers are used, the narrative must document controlled, manipulated, and constraint variables, prioritization of objectives, APC interactions with base-level control and supervisory systems, operating limits, failure handling, and fallback behavior, interface with online optimizers if applicable. Although final APC tuning occurs after startup, the PCN must include all known control goals, variable mappings, and constraints during the definition phase. Non-control ODS applications. Many calculations are performed for operator information or diagnostics, even if not directly tied to control. These may include equipment health monitoring, inferred properties, or performance indicators. If these calculations are not shown on PEFs, they are documented in the PCN. Algorithms, assumptions, and data sources must be clearly stated to support troubleshooting and recalibration. Integration of interconnected subsystems. When a control scheme spans multiple vendors, e.g., turbines, compressors, generator controls, a unified functionality overview narrative is required. It describes how signals pass between subsystems and how the overall control strategy is maintained. A supporting functionality overview diagram must show all subsystems, signal types, directions, and associated tag information. This ensures that integrated applications maintain deterministic control across physical and vendor boundaries. Deliverable PCN must be built in an automated, version-controlled format. Standard word processing features such as automatic headings, cross-references, and embedded figures are mandatory. All tag numbers used in the narrative must align with current engineering databases. Logic and loop diagrams must conform to project symbology standards. Once finalized and approved, the PCN becomes a key part of the plant's official documentation set, enabling structured FAT-SAT testing, startup validation, and long-term operational support. Detailed control narratives for complex loops. Purpose and applicability. Detailed control narratives are developed for all complex control loops, those that cannot be fully or unambiguously understood from PFS or PEFs alone. This includes loops involving advanced logic, multivariable inputs, calculation-based outputs, or non-standard implementation strategies. The purpose is to provide clarity on functional behavior, implementation logic, operator interfaces, and supporting rationale, ensuring successful configuration, commissioning, and troubleshooting. A loop is considered complex when it goes beyond basic control structures such as master-slave cascades or single-input overrides. Loops with calculations, nonlinear dynamics, mode switching, or subsystem interactions also fall into this category. Even simple loops may require detailed narratives if they operate in a critical process context or depend on multi-unit coordination. Content structure and narrative elements. Each detailed loop narrative is structured to provide the following. Objective, a clear explanation of what the loop controls and why it is needed. This section outlines the process risk or efficiency objective being addressed, such as temperature stabilization, feed maximization, or quality control. Functional description, a technical explanation of how the loop operates. This includes tag numbers, valve actions, set point behaviors, interlocks, and dependencies on upstream/downstream variables. Reference to associated PEFs is provided, and where relevant, the logic across vendor boundaries is explained. And implementation aspects. All relevant operating modes are described, including startup, initial conditions, loop activation procedures, default states, normal operation, steady state loop performance and expected behavior. Crippled mode, defined fallback or degraded modes if key measurements fail. Shutdown, loop actions during planned or emergency shutdown. Calculations, any equations, estimations, or data conversions involved. Constants are listed along with their derivation and data source, e.g. datasheets, flow sheets, vendor curves. Initializations, logic required to bring the loop online without causing upsets. Interfaces, signals to from other systems, e.g. compressors, IPS, ODS. Operator interfaces, what the operator sees, manipulates, or overrides, including faceplates and display expectations. Special considerations, additional logic like tracking, wind-up protection, or override logic. Each of these elements must be addressed to the extent possible during the definition phase and fully completed in the implementation phase. Control diagrams and visual support. Each complex loop must be accompanied by a control diagram formatted to match project symbology and placed at the end of the PCN document. These diagrams provide a graphical representation of the control logic, including signal flow, fail-safe positions, mode transitions, and instrument placement. For plant-wide utilities or priority control schemes, e.g. steam, nitrogen, overview diagrams must be included even if they involve only single-loop controllers with dispersed implementation. Tagging and referencing standards. All tags must follow project tag conventions. Intra-unit tags may be referenced without prefixes, while inter-unit tags should retain full identification. Service descriptions must be included to ensure clarity for commissioning teams and control system integrators. History and modifications. A brief history log is included for each loop to record changes in design, implementation, or rationale across the project lifecycle. This ensures traceability and helps avoid reintroducing failed logic in future revisions. If no changes occurred during development, the section is left blank during the definition phase and updated as needed post-startup. Timing and deliverable expectations. The functional structure of each loop narrative is developed during the definition phase. Implementation details, such as timer settings, operator interface behavior, and calculation constants, are added during the implementation phase once vendor data and engineering tools are fully available. This level of documentation ensures all complex loops are fully understood by design teams, properly implemented by control vendors, and operable by plant personnel under all conditions. It supports rigorous FAT, SAT, and operational readiness activities and becomes a long-term asset for safe and efficient plant operation.